Thank you, everyone, for coming. Welcome to this session. Today, we're going to be talking a little bit about classifying galaxies and using, as it turns out, supervised and also self-supervised networks to learn how to classify merging galaxies. So I wanted to introduce myself. I'm Dell'Antonio. I'm a professor at Brown, and I'll be talking about the science bit and a bit about the module. And I also wanted to introduce Philip LaDuca, who's a student at Brown and is going to be a co-presenter, but he's also, most importantly, the head developer, the person who actually wrote the module and has the expertise on this type of self-supervised network. As you'll see, once we get into the module, we have both a supervised and a self-supervised network, so you can compare the behavior of both and what needs to be done. And we'll talk a little bit about what makes one network useful versus another, what makes one network easier than another. But to begin, I wanted to motivate a little bit the idea behind the module. So galaxies are really important. They're important for understanding galaxies, but they're also important for cosmology because they're the basic element of cosmic structure. So matter in the universe isn't randomly distributed, and the basic set of in which the galaxy is distributed between the matter is distributed is in galaxies. It turns out not most of the matter is in galaxies, but the most readily identifiable objects. So if you've ever seen a plot that looks like this, one of these redshift diagrams, each of the individual dots represents an individual galaxy, and you can construct maps of the large-scale structure from these mostly distinguishable systems. Galaxies are different from, say, electrons or other things in that they are fuzzy, and they often intermingle. And so we'll talk about what makes that a challenging problem from a classification point of view and from an identification point of view. So first, what's in a galaxy? I have two examples of galaxies from the data set that you'll be looking at. I actually think neither of these are in the subset of the data that you'll be classifying in the notebook. But you can think of galaxies as collections of stars, gas, dust, also dark matter, that are collected together and are under mutual self-gravity. So they're held together by gravitational forces. They come in many shapes and sizes, but most galaxies can be characterized as either spiral galaxies, as you see on the right. They have active star formation. They have disks. They have these bands of star formation called spiral arms. And elliptical galaxies, which are much more blobby, don't have a lot of star formation, and are composed of a single component. There are, of course, galaxies in other categories, and one of the interesting parts of the classification is to find the things that are different. So one of the things about galaxies is that they interact way more than stars do. Stars are the things inside of galaxies, but stars inside of galaxies mostly don't collide. The reason for this is that the typical size of stars is large, but very small compared to their separation. So typical size of a star is somewhere between 10 to the 8th and 10 to the 10th meter between smallest dwarfs and large supergiants. But their typical separations are order 10 to the 17 meters. And that gives you a separation to size ratio of something like 100 million to 1. And that's a very large number. So even though the galaxy crossing time for a star is much smaller than the age of the universe, their relative size compared to the separation makes it unlikely that any collisions happen. You may have heard that there are these models in which the Milky Way and Andromeda will collide. When that happens, something of order 1 out of the 100 trillion stars in each galaxy will hit another star. So not a common phenomenon. There are a few situations where these interactions are more common. The centers of globular clusters, we're going to ignore that for now. However, the key point that I want to make is that the situation is completely different for galaxies. Galaxies' sizes vary a lot, but a typical galaxy is a size of something like 10 to the 20 meters. But the intergalaxy separation is only 100 times for that. And so even though galaxies take longer to cross the distances, 10 to the 9 years instead of 10 to the 8 years, or the probability of galaxies to merge is very, very high. And in fact, most galaxies have undergone a particular merger event or some sort of interaction. In fact, we'll see that if you consider the mergers with very small galaxies, essentially every galaxy is undergoing these events. So galaxy collisions are common, and galaxy collisions are extremely important. They're also much more common in the past. If you think about an expanding universe, the distance between galaxies is growing, at least in the distant past. And so in the past, the galaxies were closer together and the intergalaxy separation was therefore smaller. These galaxy interactions are really important for a lot of the evolution of things that make galaxies galaxies. They're responsible for triggering bursts of star formation. They're involved in the evolution of one galaxy. So collisions can take spiral galaxies and turn them into elliptical galaxies. They can replenish the gas supply sometimes or drain it sometimes. And they make galaxies grow. So it is one of the mechanisms by which galaxies become larger. So it's important to find galaxy interactions. The interactions and their effects are long-lasting on a human timescale, order 100 million years. And this is a very awkward time because my lifetime and the lifetime of any graduate student thesis is much, much shorter than 10 to the 8th years, and hopefully will forever be. But it is much shorter than the age of the universe. And so so even though most galaxies interact, most galaxies are not having a major interaction at any particular point in time. So the long lifetime means that you can't follow a single galaxy's interaction through its entire lifetime. You have to catch galaxies interacting in all different phases by studying different galaxies and construct samples of different galaxies to study how galaxy interactions work. And so that ultimately is why large samples of interacting galaxies are important. So galaxy interactions visually are very spectacular things. So they can have many different forms. One classic type of them is the result of tidal tails. So when two galaxies come together, a close encounter of one galaxy with another galaxy of similar size or larger size, some of the stars are actually stripped off by tidal forces, creating these long tails of interactions. These interactions remove some stars from the galaxy, and they can float and become stripped from the individual galaxies to become part of what's called the intercluster or intergroup light. But they can also increase the kinetic energy of the stars in the galaxy, puffing it up. And one of the interesting things about gravity is that if you decrease the gravitational binding, you also decrease the typical kinetic energy. So the stars actually start moving slower, even if their radius is larger. So you've given them energy, but they become colder. Another type of interaction that happens a bit later when galaxies merge is that they maintain memory of these tidal interactions. And that can result in tidal shells. So these happen when the stars expand out, and then at turnaround, when the gravity holds them back, they start collapsing. But of course, in a gravitational field, you spend most of your time further away. And so you get this enhancement in the density field at the turnaround radii. And so this is another indicator that galaxies have been interacting. All of these examples come from the image survey that we'll be talking about, which is run with the 4-meter telescope on Cerro Tololo. And so there are particular examples that would be in the sample, but of course, because of some sampling, some of these are not in. You can actually figure out how many passes have happened before merger just by counting the number of shells. So it's an interesting way of recovering the history of the mergers. Another particularly interesting to me form of this is that sometimes the interactions involve the galaxies and the gas that's between the galaxies. So the gas in galaxy clusters is very, very hot. And so when galaxies pass through this gas, the gas in the galaxies feels a very strong ram pressure stripping, which drives the gas out. And so the effect of that is to create these streamers of gas. This is why they're called jellyfish galaxies. And in these streamers of gas, the gas shocks and clumps and forms these star-forming bursts that you see as these blue knots within the streamers. The interesting thing about this is this also gives you a time scale, because the length and the color will tell you the velocity of the galaxy through the medium. And this turns out to be really important from a cosmology point of view, because galaxy motion, since galaxies take about 1 billion years to go through across a cluster, you can't measure the transverse motion directly. You can recover the transverse motion from the tidal features. So that's a basic idea behind why this is an interesting problem. The second part of the introduction is related to why surveys are necessary to find interacting galaxies. And again, this has to do with the time scale. So galaxies interact, but because mergers only last 100 million years, that means at any given point in time, many fewer than 1% of the galaxies are interacting. And this means that catalogs of galaxies where we have to catalog all the phases of the interaction requires looking through many, many, many galaxies. And since there are many different types of interactions, reconstructing the physics on average requires millions, or to propose many mass ratios, billions of galaxies. The need to find interacting galaxies in surveys was recognized very early. And already in the late 1950s, Zwicky and Vorontsov-Velyaminov actually combed through photographs of tens of thousands of galaxies to create the first samples of interacting galaxies, where they found a few hundred. Between the two samples, it was actually less than 1,000 interacting galaxies. Enough to notice that this event happened, but not enough to do a reconstruction of the physics. The problem is that as surveys have measured more objects, they've gone from thousands of objects, the Zwicky catalog contains about 30,000 galaxies, to millions of galaxies, that's what's in the Sloan galaxies, to billions of galaxies, that's what's going to be in the LSST catalog. And the number of objects to be observed dramatically increases. The diagram I'm showing on the right shows a measurement of, as surveys have grown, the area of depth of covered times the depth in magnitude. So to actually get the number of galaxies, you sort of scale it by the area times 10 to the 0.4 times the depth. And so the next generation of surveys will have 200 to 500 times the number of galaxies, the millions of galaxies in the Sloan catalog. And that becomes a very difficult problem. It took Zwicky a long time to go through 30,000 images. No one will want to go through 1 billion images. Or certainly not a single person will want to go through a million images. For the Sloan survey, at the level of millions of objects, there has been a lot of progress using humans. And people are, to their credit, very, very good at finding interacting galaxies. So here's a sample of interacting and some non-interacting galaxies from the Sloan survey developed by the Galaxy Zoo project. And what the Galaxy Zoo project did was enlist volunteers from the public to classify images. So that basically, instead of leveraging AI, it leveraged real intelligence, people. And one of the things they discovered is that they were willing to get thousands of volunteers. And at the result of this, about 1 million galaxies were classified from the Sloan by many people. In fact, part of their verification technique was to have multiple people classify the same galaxies. And they found something like 5,000 interacting galaxies in the Sloan survey and in the extension to the CANDLE's Hubble survey field. At the level of millions of galaxies, this is still possible, especially with the growth of the internet. Getting 1,000 volunteers or a few thousand volunteers is possible, but getting 100 times the few thousand volunteers is a very difficult order. And so you need a different strategy if you're going to do the same classification on the billions of galaxies that are coming up. And so this is why machines are going to be doing the classification for us. Oops. I do want to point out that this is not at all an original idea. If you go to the Astrophysical Data Service, which maintains a record of astronomical papers, and do a search on machine learning galaxy classification, you find that the papers listed, you find a lot of references to papers And in particular, you see a huge spurt in papers. I'm actually not sure what the papers in 1993 and 1995 are. I suspect there was other words that machine and learning were not next to each other in that for those particular papers. But the things since 2010 show clearly the vast explosion in the papers on machine learning galaxy classification. And so this is something that many researchers across the world are actually very actively working on and trying very different techniques. So, for example, even in the last 6 months, there have been papers by Abraham, Ferreira, Desmonds, Margalef, Bentapol et al., all talking about galaxy interactions in machine learning. The implementations we're going to show you, particularly the self-supervised one, is based on Desmonds et al., but you can and you should look and explore other classifications. So there's no idea that there's right now a perfect classification that will classify galaxies better than others. So at this point, I'm going to introduce the idea behind what we're going to be doing, which is supervised and unsupervised machine learning. And I wanted, before we go to the notebook, just to do the ground rules. The basic idea is supervised learning is a basic form of deep learning in which a pre-trained set of classifying objects is given to a model, and the model is directly trained using the classified images to learn by itself the rules. So it's supervised in the sense that you are giving it the training set first, and then you apply the rules to some second set. Unsupervised learning, self-supervised learning uses the label without, so it does a first part of the training without any labeled data, allowing the model to build its understanding of the data itself by comparing images to images in an embedding space. In our particular case, we'll talk about using a contrastive learning to train the model to find similar objects. Then once they've been trained, you can then train it on labeled data to fine-tune and create a labeled version. But the great advantage of this is that it has a particular strength, which we'll talk about at the end. So at this point, I'm going to pause the demonstration and ask people to access the notebook. And I'm going to start sharing. So this is not exactly the notebook you're going to be running, but it is the same steps. The only thing is that files aren't going to be saved, so you will need to make your own copy as instructed in the instructional manual. So we're going to run through the steps, run through a few steps, discussing what the notebook does and starting the supervised training. One of the things about training and things about this workshop is because we're using CPUs, basically the things that Google Colab makes available by default, training a large data set is a time-intensive process. And so you will not be fully training a set. You'll be running through a few training steps, but you'll notice that the improvement in the training will be moderate. So the very first step is simply just uploading the UMac Learn package to bring up the core bits that are going to be used. And we're also going to import the libraries. Because this is an astronomical software analysis package, in addition to the machine learning packets in sklearn and TensorFlow, we're also installing parts that involve dealing with astronomical images from AstroPy. But those should all be importable through Colab. It will take about a minute for this first import to work, but it's not a particularly long step. So we'll just wait for a second for this step to finish. Yeah, so there was a question about, oh, no, it's been answered. Okay, so that took 39 seconds, not too bad. One of the things that you'll want to do is, in order to be able to save your own version of the output, and that will be important for submission, is to run the steps of mounting the drive and creating your own paths. If you've been following the winter school before, you should have this set up, and it will basically create this module 4 entry for supervised learning, and that should be all set up. I am not going to run this step. because I'm not going to be saving my files to submit. So it should work without doing that save. But
Wait,
oh
Jan,
no,
you
no, I
should,
actually do need to run this, don't I?
yes, and the step that you'll be skipping is commented out here,
Okay,
but
perfect.
for the student collab, it will be uncommented.
Okay. So you should get all this stuff. So that highlighted the fact that I'm not actually at Brown to run this module. Okay, this is the step where you'll see that my version is commented, but yours is not. Okay, so now you've hopefully will have set up your systems to be able to write and save the output files to your parameters. The next step is to talk about what the data looks like. And so I'll run through the steps quickly, but then I'll describe them more slowly in the slides when we go to the slow step. The way the classification works and the way astronomical images are taken is the CCD cameras that take the images are intrinsically black and white. And so we use filters to collect light in different colors. And in this particular case, we have 5 separate images of all the objects through ultraviolet, green/blue, red, very near infrared, and only slightly less near infrared channels. And the network gets all of those images in order to try to figure out the values. And you can see that there are a few other parameters, noise range and jitter max, that have to do with the input training set. So I'm going to run this. This should be very fast. It just defines the parameters. Just to give you a sense, and there are figures in the slides, the basic idea is that you want to be able to distinguish galaxies that look like this, which are spiral galaxies, from galaxies that have shells, like this galaxy. And with a little bit of practice, the human eye is can very easily determine galaxies that are interacting that are not. But of course, the computer does not know those things. And so it's become impractical for doing this. We're going to run this 2 different versions of the network. First, the supervised version, and then an unsupervised version. And so first, let's define the functions. And then load in the data. In this particular case, in order to make the run times manageable, we're loading only 918 images with associated labels that have been classified. My students and I, at the beginning, when we were slightly more ambitious for this workshop, had classified about 5,000 galaxies, and then it turned out to be too slow to load and work with all that data. So we're working with a small set. I will highlight that the full data set that's available from this particular study is another factor of 20 larger than that. It's about 100,000 galaxies from even this small survey. Okay. So the loading, again, should take you a little bit of time, but not too long. This loads up the individual 5 images for 900 objects, but it does not do yet anything in terms of the training. And the reason for that is that if you load the images and ask a network to train on those images, what you will discover is that there are lots of things that make galaxies different from each other that have nothing to do with interactions. Galaxies have different sizes. They have slightly different centers. They're rotated if you take the same galaxy and rotate it. And so to do a training, you actually have to do an augmentation. And so here we're going to define different augmentation functions. One of them is adding a different noise to the image. One of them does a different cropping of the image, so effectively shifts the centroid of the image. And the last one does a shape and inversion and a reflection to mimic the effect of rotation. One of the things to be careful about when you do rotation is that, unlike reflections and shifts, which preserve all the pixel noise data, rotations produce correlations in the background pixel noise, and you have to be careful not to make sure the network doesn't train on rotation, on the pixel noise correlations that are induced by the interpolation of rotation. So in this particular case, we're not. In a case where you wanted the accuracy to be larger, you would have to deal with that. Okay, so now once we have this, I can just display some bits, and you should be able to display on your images some bits of the axes. And hopefully it will run and display some images. Okay, and you'll see that a set of images have appeared with the original image on the left and one of the augmentations. So effectively, we've created a data set that's much larger than our initial data set by including sets of shifted and original images. This will become quite important for self-supervision, because in the self-supervised model, it knows that these augmented images are the same as the initial image. And so it will work to try to keep them in the same parts of the space. So here's a case where the image has been shifted, cropped, and flipped. And here's one where it's been mirror imaged up and down. And here's one where it's been shifted and expanded. So now that we have the augmented data sets, we're going to start one of the supervised model. The convolution model that we're doing for supervised basically runs a network that reduces the size of images by finding layers and weights of layers to flatten the image data and pass it into other layers. And then it uses a sigmoid activation function to follow the output into a binary classification. Remember that this is the supervised model, so it's trained, it knows which things are not and which things are not. Again, in a typical supervised set, you would be running this through many iterations where it would learn the training and learn to improve the models. In order to keep this under or around 10 minutes, we are going to have it run through 5 steps of training and just demonstrate that it does improve the quality. It uses what's called an atom optimizers, which uses the changes in the different variables to update the weights, and then binary cross entropy as a loss function for the classification test. So I encourage you to press this button, and then we're going to shift back to the slides, because this step is going to take something like 10 minutes. So the idea behind the notebook is we're going to look at this data augmentation, we'll finalize the training, now we're training the supervised model, then we're going to explore an embedding space for the unsupervised model, for the self-supervised model, and then we'll talk about classification at the end. To talk a little bit about the data that you'll be using, this data comes from a survey that we at Brown and a few of our colleagues are running called the Local Volume Complete Cluster Survey. It's a survey of 100 regions of the sky around the most massive clusters in the nearby universe, where nearby is a relative term. It means within 1 billion light years. So much less than the size of the universe, much less than the age of the universe. It's about 500 square degrees, 200 full moons worth, and measures about 200 million galaxies, about 2 million of which overall are big enough to ambiguously measure the shapes for. So you'll be working with data from 3 clusters, actually only part of the data from 3 clusters, in order to keep the data volume and training times short enough to fit in this period. So the training set consists of images taken from clusters Abell 2029, 3667, or 85. For those of you who care about those things, don't worry if the names mean nothing to you. The data comes from the dark energy camera, which, as the name implies, was used to run the dark energy survey. It's on the Blanco 4-meter telescope in Chile, and it's been collected over the last 6 years as part of this survey project over the course of about 100 nights of telescope time. And you can see a picture of the telescope camera there. For each cluster, we're using postage stamps I said 200 by 200, but it's actually 300 by 300 pixel images extracted automatically. So there's a non-AI program that selects all the bright objects in the image that don't meet a criterion for being stars and automatically extracts the same region of the images in each of the 5 different filters. So a combination of those filters, the G, the R, and the I band filters, has been used to make a color image at the right. But the network really has the 5 black and white images rather than the color composite to work with. Again, 3 members of our group have tediously looked through a bunch of things and classified them. And this is important because the supervised learning desperately needs the truth value to train in the network. And that is the downside of the supervised learning. You will need a very large train set beforehand before you do anything with it. So in order to train the model, the galaxies and tidal feature galaxies have to be you need a model that has both. And in a balanced data set, half of them are labeled one and half are labeled the other. Remember, why might it be important for a data set to have a balance? Well, if you remember at the introduction, the number of interacting galaxies is much less than 1% of the overall galaxy. So if you just feed the entire sample without doing any training, we will have many more galaxies labeled 0 than 1. So the set you're working on is a set which has been biased for training towards having more interacting galaxies. Again, this is something that is necessary for the supervised networks to do their job. As I mentioned, augmentation is important because networks do not know, unlike human brains, that a galaxy that's been rotated by 90 degrees is the same galaxy. And so you need to have a wider distribution of data to improve the modeling accuracy. And so we create these models to make it more robust to noise, orientation, positions. And that allows it to help, once it gets data that hasn't been seen, to not say, oh, this is a galaxy that's rotated 12 degrees. I had an interacting galaxy that was rotated 12 degrees. Must be an interacting galaxy, when it has nothing at all to do with it being interacting or not. So the idea is you do this augmentation to prevent the network from fitting for something that is not important. And so part of the work of augmentation is to decide which things you think are important, which things are less important, and to train for those things versus not. So as I said, for this particular set, we have chosen to only do 3 different forms of augmentation at the cost of a little bit of accuracy. We are only doing random horizontal and vertical flipping. We're adding a Gaussian noise, so there's no correlated noise added. And we're doing a random cropping rather than doing a shifting. So there's no rotation, we're not adding any or subtracting any extra features to our objects. So as the supervised model is running, what the supervised model is just a convolutional neural network. So the layers are just convolutions that run filters across the images to reduce the dimensions, to get some features in the image. And then each of those convolutions is given a weight, and the length and width of the images are reduced in order to increase the time. Then this ReLU method is used as an activation function. The other thing that gets done is what's called batch normalization to help stabilize the model. Once the dimensions are reached small enough, then you pass the images through a linear layer to classify it, as I said, at 1 or 2. And so the sigmoid activation is used to calculate the activation function. And then the loss function is calculated through binary cross entropy. It is still running, but you'll notice that it's actually it printed out the parameters for the individual things, so exactly what it's doing for normalization. And at the bottom of the screen, it's actually telling you what it's doing for each epoch. And it has just reached epoch 5 of 5. So it's a bit more than 80% done. And you can see that the accuracy is not spectacular. Again, because it's only using 900 galaxies and you're only doing 5 training steps, it will do slightly better than random, but not particularly hugely better than random. So it's now a third of the way through the last pass. We're going to let it sit through the last pass and then pass on to the next step where we're actually going to plot the values that it's come up with. So one of the advantages of supervised networks is if you do have a large training set, they are simpler to set up and they sometimes perform quite well. And so if you find yourself with a large training set, this might be a good strategy for you for running a network. Only a few things left to do once it's gotten through batch 5, so it should be within the next minute or so ready to go on. In the meantime, there's a question on whether there are other data augmentations that are applied aside from the basic ones. So depending on what you're interested in picking, one of the things that you can do in data augmentation is add random other galaxies in the field to make sure that that the presence of a second galaxy in the field doesn't bias the classifications. Okay, the model has trained. So let me go on to the next step. Okay, so once we've trained the model, and each of you will have a slightly different training loss function, you can see that the training loss, of course, since you're using the same training set, stays relatively constant, but in the validation set as it runs, it does better. And in this case, the accuracy did not do that much better, but it will if you train it for many more steps. Okay, so that is our basic introduction to the supervised method. The supervised method, these types of supervised classifiers, in one form or another, have been popular for the last decade, and so it is not something that is particularly new. One of the things that we did want to feature, however, is a self-supervised model. And the thing about self-supervised models is that instead of giving it a trained system right away, you give it all of the images and have it, the model, try to arrange the space in some sort of feature space to find similar or dissimilar objects. And the basic idea is you give it an input set of objects, it runs multiple random augmentations of different galaxies, then it does an encoding of each one, knowing that these are the same galaxy. And then as it runs, it starts adding nearest neighbors in the encoding from different galaxies to try to find neighbors in this set. So you compare to all the other samples, the nearest neighbors, you do a contrastive loss, which basically minimizes the distance between embeddings and neighbors, and eventually it finds all of the galaxies that are most similar to each other. So we're going to define the parameters for the self-supervised network. This is a fast step.
Jan, there's a question about the different wavelengths for the bands of the images. Do you want to talk about that real quick?
Yeah. So the filters defined are the same filters actually used for the Sloan, although there's slight differences having to do with the fact that the detectors are slightly different. So the U filter is basically near ultraviolet. It covers wavelengths from about 350 to 450 nanometers. Each of the filters takes a band that's about 100 nanometers wide of light. And the idea is that each of them encodes different information. So the U filter contains information about very recent star formation, the distributions of the bluest stars. By contrast, the Z filter, which is roughly 900 nanometers to 1.1 microns or 1.05 microns, contains information about the reddest stars. In interactions, different interactions create different mix of star formation. And so different types of interacting galaxies will be characterized by different features, but also different types of galaxies at different amounts of star formation. And so the colors of galaxies can vary. And the idea is that rather than giving it the catalog properties of galaxies, it is better to give it the images and have it figure out those values. So hopefully that's enough of an answer as to why the filters are. The filters, I mean, we'll say the filters span the entire optical range. So they're picked to have many different values, but not so many that we have to spend an immense amount of telescope time. There are projects that image the sky in more filters, but they tend to cover much smaller areas because you have to take more time imaging in more filters. So here we're defining our encoders and the self-contrastive network. And then we're going to run the model and go back to the slides because this one's a little bit faster. It's not actually doing the classification yet. It's going to just create the shape model. So let's set this running. So the self network does also rely on a convolutional network, projecting the data into an input space using what's called a ResNet model, which is a model for computational networks. And the idea is that it learns these embeddings for the galaxy images and then creates this network at the end encoder, which takes the inputs and will produce a classification. But the idea is that once you've had the encodings, you have a set of galaxies that know where the network knows which galaxies are similar to which. And one of the great advantages of self-supervised networks, oh, sorry, let's talk about the training first. So to judge the similarity, we have the models create these augmented images and then basically creates the contrastive loss first to attempt to maximize the projection, that is the similarity between the embeddings of the same object, and then compare the most similar embeddings from other images to the data set to group images of different galaxies that have very similar characteristics. And then it creates this spacing in which in the space it has galaxies that are close in those embedding spaces are galaxies that it thinks are similar to each other. Obviously, the more it trains, the better it will get at getting that measurement. And the more galaxies it has, the more it fills out this embedding space. So what we're going to do once we have the self-supervised method as training is to explore the embedding space. So using UMAP, which is a tool to project the higher order embedding spaces into these two dimensions, you can graph the embedding spaces and then plot the images to see, well, what did it think was similar to each other? And that's actually a very illustrative thing to have this embedding space stored. We'll be storing the embedding space. One of the things to mention is that as you run the notebook, because the training is different for each of you, the projection is slightly different for you, and each of you will see a slightly different projected map, and that's fine. So in this particular case, our embedding space is much higher dimensional than we can project. It's not easy to see 128 dimensional space. So we're just going to pick the two principal components, the two most important components that it found to embed. So once this is done, we'll project onto those components and plot the distribution. It's taking about 10 seconds per step, so it should be about a little over a minute away. Getting close. You should also note that we're cheating a little bit here. We're not doing the full on self-supervised training. This is slow, and if you do this, you definitely do this with a GPU rather than a CPU. But we could not guarantee that every user, every attendee would have access to a GPU, and so we did not want to make a module that depended on it being GPU enabled. It's now just wrapping up. Testing this morning, this took 5 minutes. Yeah, 5 minutes. Okay, so we're going to project into 2 dimensionals. And then we're going to have to add to the self-supervising encoder a classification head. This is where the classification comes in this model. And one of the great things to highlight is that the self-supervised part, the initial part, does not know what we are interested in. So if you are interested in different things, you can just change this part. And then the rest will be able to classify different types of things that you're interested in from the same data set. So this is a way of multitasking. Okay, so now we're going to run this step. I'm going to run it and then explain what it's going to do. So this is going to create an image in the embedding space at the positions listed by xval and yval. So the red dot at xval, it then selects the 5 galaxies that are most similar to that are closest to that point in that projection of the embedding space. So if you want to change this, for example, let's say I'm interested in things that are at x equals 8, y equals 5. I can set xval equals to 8, yval equals to 5, and rerun. And this step is relatively quick, and it will go and find the new versions. It will show you, the 5 galaxies that are closer to this. What's interesting, there's a galaxy, there are a pair of galaxies, both of which are in the data set. So you'll notice that the top right and bottom left in this case are similar because it's really the same field. And so it's good that it found them as the same object or very close to each other, because they are very close to each other in space. On the other hand, you can see that on the top left panel, it did find a galaxy that has a tidal tail. So I encourage you to spend a little time playing with this coordinatization and seeing what things you find. Because once you've found a set that you're happy with, we'll proceed to the next step. You should also write down the values and print out the model accuracy values. So those you will be part of your submission. So when you run the next step, you'll want to save those steps. Let me do one more just for maybe, let's see what's at x equals 11, y equals 9. Often the extrema of this space are often places where the most odd things are. That does not mean that they are the most interacting ones. They could be odd for a different reason. Remember, this doesn't know that they're interacting versus non-interacting. All it knows is that there are things that are different from each other. Yeah, so this has found things where there's a ring in the image, but some of them are normal spirals and some of them are spirals that are projections. The bottom right one is a tricky one because they're actually 2 galaxies superimposed rather than a single galaxy interacting. But again, play with this. This is your chance at customizing this a lot. Oh, I did find a particularly messy one. Okay, so once we have galaxies that look like this, we're going to be running the evaluation based on the model on these systems. And you notice that supervised model actually did better. It found all 4 galaxies and classified properly, and the self-supervised model did not do as well. Partially, this is a training issue. Partially, this is chance. The level of training that we've done, the accuracy over the whole sample is something like 65%. It's not huge. But you can actually see which galaxies were predicted to do well and which galaxies were not predicted to do well. And so in this case, the supervised model, the true classifications all listed them as green. The supervised model all said that, so these were all non-interacting galaxies, and the supervised model called them non-interacting. In the self-supervised model, it actually found these as interacting and found them as interacting in an interesting way. So these are galaxies that are superpositions. So again, this is where a data augmentation that had superpositions of galaxies would have helped the self-supervised model more than the supervised model. It's because the supervised model knew that these were labeled as non-interacting, it would have done better with this. Okay, let's go back to the slides. But in the meantime, for those of you who are interested, just keep playing with these selections and see how you're doing. And again, what you will be submitting is this embedding space image and the model accuracies. We've been exploring the feature space, and the idea is that images that are near each other in different regions shows how the self-supervised network found the groupings. And so, for example, we learned that a better augmentation would have removed some of the grouping that it found for things that have a neighboring galaxy nearby. Those are the things that are useful when you're returning these embedding spaces. And one of the great values of something like UMAP, which will tell you what the self-supervised network is doing. So before we go on, I wanted to highlight that this is a work that is in progress. We are going to analyze the entire data set. So the notebook was trained on much less than 5% of the data. And in fact, we are still in the process of using the Blanco telescope to image these clusters. So there's plenty more data to be trained on. The other thing to note is the images were scaled so as to be normalized so that the peak value pixel was 1. And it was scaled with a linear normalization. But there are other normalizations that can be used, in particular normalizations that increase the weight of lower surface brightness features over a galaxy nuclei could yield better results if you are interested in particularly low surface brightness features. So one of the things to be careful about is how you input the data and what bits of input data you are feeding. You don't want to fit the raw pixel intensities, because then classification will take galaxies that are bright and classify them differently as galaxies that are faint. So creating a range that's normalized is a good idea, but the choice you make for the normalization is actually quite important in this case. So I did want to also highlight a little bit about what you get out of this. So with a sample of interacting galaxies, you can measure things like the projected length of the features. So example at right is one of the jellyfish galaxies in Abell 85. And the length of the feature tells you a projected distance, because we know the distance to the galaxy cluster. It turns out we can use the color of the features to tell you an interaction time, because the stars that get formed, the blue stars that get formed, have lifetimes that are shorter than the jellyfish timescale. And so you can get a variation in color. Another way of doing this would be to obtain a spectrum, because you can actually see the emission from star-forming regions, and you can get the age of the stars that are in the features based on those features. But if you combine a length and a time, you get a velocity. And velocities transverse are very hard to get in other ways. If you get spectroscopic measurements, of course, you get the vertical velocity from the redshift, but that's a much easier measurement. Measuring where interacting galaxies are gives you information about the conditions. What makes these features happen? Is it galaxy density? Is galaxy relative velocities? For example, It's been found in studies with Sloan that the interacting galaxies are actually slightly more common in groups than they are in clusters. And the reason for that is that the relative velocities of interactions are slower, which means the interactions last longer. So it's not that the interactions are bigger, but they last longer and create larger tidal tails, and so easier to see. Meanwhile, jellyfish galaxies are more common in galaxy clusters because they depend on the gas density, and the more material you have, the larger the gas density. So those things can all be extracted as the output of a network. So the network is telling you to find the objects, you then use those objects to do physics. The other thing about unsupervised methods that makes them particularly, or self-supervised methods that make them particularly effective, is that these methods find things that are different, but you can use the same training. And I realize I never changed unsupervised to self-supervised, which is a more technically correct term for this. You can use the self-supervised training to train objects, the images, the full set of images and the full augmented set of images to find similarities, and then have a classifier classify different types of things from the same training. And the idea is that you can find new and different types. So for example, there are things called polar ring galaxies, which are a long-term remnant of galaxy collisions where you have one galaxy and at large radii, you have the remnants of the second galaxy more stably added. Those things are rare. I will say I didn't pick the most rare example. Right now, we know of about 50 examples in the entire universe. But certainly many more of these will be discovered. And it's just one of the class of things that a self-supervised network can reach. So you basically spend more time, and you'll see that per cycle, you often do less well with a self-supervised network. But then you gain in flexibility later. You can actually have the self-supervised network measure once and cut many times and figure out different samples of objects. It can also tell you about galaxies that it thinks are fairly normal. So again, you can figure out one of the classic results of Galaxy Zoo was the fraction of galaxies that were clockwise versus counterclockwise. That's something you can have the grouping figure out for spiral galaxies. So I did want to also highlight that there are some huge applications to this project. The future surveys will create the number of objects that is greatly larger. So particularly the Vera Rubin Observatory, which is almost ready to begin its 10-year survey of the sky. In a month from now, tomorrow, I think, the 3 gigapixel camera is going to be installed on the telescope. For many, many years, I would show a diagram of the model of the telescope. This is an actual photograph of the telescope. And so you can actually see that the telescope is set. We've actually taken data with a smaller camera on the same telescope. And this survey is going to take many millions of images. Actually, the images that you'll see will be built from huge strings of 30-second snapshots. So there'll be lots more data. And you could imagine training on differences between snapshots to, for example, change the noise parameters. It's a much larger telescope than the data that I was showing in this notebook. And the survey will go about 10 times in flux deeper and cover an area 50 times larger. So the number of galaxies will approach 50 billion. Now, there's an asterisk there. Some of those galaxies will be very small. And so if you wanted to look for interacting galaxies, it's a much smaller data set, but still a much, much larger data set than you can reach from even citizen science. One of the issues with the LSST data set is that a very large number of the galaxies will be too small to resolve. And to get around the issue of resolution, you can go to space. And so NASA has worked on the Roman Space Telescope, which will conduct a survey of about 2,000, interesting line break, 2,000 square degrees. This still says example because the panel that is deciding what exactly Roman will do is still convening. But the idea is the Roman Space Telescope is a clone of the Hubble Space Telescope and produces images that are of the same quality, but with 500 times the field of view. So create a lot of images. And so the Hubble, for example, the largest area it has ever imaged is the Cosmos program, 1.6 square degrees. It took thousands of orbits of, well, more than 1,000 orbits of Hubble time to generate this data set. And the Roman Space Telescope will generate about 2,000 times as much data in the first 5 years, contiguous. So being able to measure objects. And so furthermore, by looking in the near infrared, you can actually look at these blue galaxy features at much larger redshifts, right? If you look, redshift is the measurement of how much the universe has expanded, which shifts the wavelengths of light to the red. For a ground-based telescope, if you're looking at things that are emitted in the U-band at 400 nanometers, at redshift 1, those are already at 800 nanometers. Things that are at redshift 1.5 are already outside the detector range. And so you can't look for the same features earlier on when we think galaxy interactions are much, much more, well, we know galaxy interactions are much, much more common. And so the Roman Space Telescope will revolutionize this field and be able to detect the galaxy interactions to a much larger number of galaxies. Even though it's a tenth the area of LSST, it will probably be able to find more interacting galaxies than LSST will. There are some limitations to this that you should know. The self-supervised methods are prone to finding differences in latent dimensions that represent nuisance parameters. I think I showed you one, which is neighboring galaxies. So augmentation has to be done carefully. And often in this development, augmentation and self-supervised running sort of are hand-in-hand steps where you run a step, you discover the portions of the parameter space that are less interesting. You say, oh, I can think of an augmentation which will allow the self-supervised classifier to think of these as the same and therefore not classify them as interacting. The classifier itself for supervised requires a significant number of classified galaxies. And this is true whether you used an unsupervised or a supervised method. For the self-supervised method, we actually use the same classification weights as we did for the unclassified. It's just the distances and the parameters were different. And so this can be very time consuming to create manually. And training a large number of images with a self-supervised network can be very, very slow. So this is a place where GPUs are really a huge advantage over CPUs. So I'm going to go back to the notebook and finish the notebook. But one thing I did want to highlight before we go back to the notebook is be sure to submit your classification and training results. I'll be looking through them and trying to see who's found the most interesting interacting galaxy. And I'll also be curious to see whether the supervised or the self-supervised network did better. So in our training this morning, the self-supervised network won, but just now the supervised network won. For this small number of trainings, which one will win should be relatively random, but it'll be interesting. You are basically creating many test cases. And so it'll be interesting to see whether you can find the measurements. Look in the README file for how to find the link. There's a Google poll where you can upload an image and your classification training results. Okay, so we had this portion of the embedding space. I'm going to pick a slightly different portion of the embedding space to try again, just to create a slightly different output. So I'm going to say, let's pick 8.5. No, I did 8.5 before. Let's do 6.5, 7.5 and see what it finds. Okay, what did it pick? It picked a galaxy that shows up twice. Okay, and then we'll do tell it what it found. Yeah, in this case, the self-supervised model did better than the supervised model. And again, this is not surprising. They're both fairly random because they weren't trained very, very long. Obviously, a larger data set and longer training will do better. And I believe you have access to this notebook, but if you're actually curious and are willing to spend 20 hours on this, you can change the number of times you train and see how well you can do. But for your submission, please submit it soon, because it's not really that important to have gotten the best classification. Okay, so we're going to create our plots. So that's the true classifications. 2 of them were listed as interacting, 2 of them non-interacting. The supervised model said they're all non-interacting, but the self-supervised model picked the interacting ones more than the non-interacting ones. All right, at this point, there are a couple questions. Let me see if there's something I can answer in the questions. The entire data set is part of Philip's senior thesis project, so I think I won't submit the entire data set. So you can train on this data set more, but so there was a question about having the entire data set. Also, the entire data set is quite large. Once you've put in 1 million postage stamps, even though the postage stamps are small, that is many gigabytes worth of data. So yeah, rather than doing that, I think keep working on this data set. And the instructions for submitting them should be in the instructions for the model. All right, with that, let me ask if there are other questions having to do with one of the things highlighted wasn't there at the beginning, but as Professor Gateskill said, the PDF copy of the slides is available in the module folder if you want to refer to them later. So you'll have access to those. Philip, are there other questions that are easier for me to answer than for you?
Someone just asked a question about image submission. Shall I read it out?
Oh yeah, it's the one that's automatically saved, right? The numbers that come from the numbers aren't automatically saved, so you have to jot down the numbers for the model accuracy. But we don't need there's a huge duplication in the final images where the same image appears 4 times or 3 times. We don't need those. We just need the one with the embedding space next to it. Because we have time and I have a little bit, and I'm curious, I do want to, one of the interesting things is each of you should see a slightly different embedding space. And the edges of the embedding space, the more objects you have, the more you will fill the embedding space. But you can see that the extent to which the volume of space is basically a measurement of the value of how accurately it was able to distribute. So if your network isn't very good at separating objects, it will reduce the dimensions of the embedding space and it won't look like a filled space. So that's another way you can know, oh, maybe something isn't going right. There's a question about identifying different objects in the same image. Right now, the training set is set so that there's one larger galaxy. There are a couple cases where 2 galaxies are very similar to each other. The way you make it not care about having 2 objects versus 1 is, again, in this augmentation step. You can randomly add other sets of galaxies that are not the central object and have it know that those are the same image. One technique of that is you can actually threshold and extract from the data images, but or if with a slightly lower accuracy, you can actually take model galaxies as create a model galaxy as some sort of disk plus bulge, and basically inject the model galaxy directly into the image. The advantage of that is that that's a no noise model, so you're not altering the noise properties. The disadvantage is that things that are very different from that, so very messy galaxies, won't be separated by the or won't be treated the same as by the augmenter. There's a question about the module submission. In the register and answer that's where you give the accuracies. Let me scroll down and find. So where it says supervised model accuracy and self-supervised model accuracy, there it's for our statistical purposes. I'm curious to see with this few trainings, which module on average is doing better. And so, on any one time, it's fairly random, but over all of your submissions, my hope is that some pattern may emerge. I can try that. So there's a question about picking an area in the embedding space that is dense. Some of that depends on the training set. So in this case, it is slightly better than average to pick a dense area because we've overrepresented interacting galaxies. On the other hand, interacting galaxies are all slightly different. So one of the other advantages of a self-supervised feature is that you'll find that interacting galaxies live in different points of this space, depending on whether they're streams or jellyfish. It will know to group jellyfish together, but it doesn't know that jellyfish are the same as others. And so then in the classifier, it figures out which features of the parameter space to pick. So let's pick a point closer to the center that's denser, like 8.57. We'll show what the galaxies there are. Okay, so that's not a very interesting thing. There's a bunch of compact galaxies, and one of them has a star next to it. That's bad. So that's the point where things that were stars that were misclassified ended up in our embedding space. That's actually another important point to highlight is that your classification is as good as the human classification. And here's one where an object that was automatically selected because it didn't look like a star. It was just a little bit more extended than a typical star, but was a star. Got through and was automatically listed in our galaxy sample. I'm just going to see, out of curiosity's sake, did we think it was an interacting galaxy? I hope we did not think it was interacting. Yeah, the models don't like this object at all. Yeah, so the self-supervised model thought that the star with a galaxy next to it was an interacting galaxy. So there's a question about if you have multiple classes of galaxies, you have to use a slightly different weighting function, right? Because a binary classification is open to slightly different sets. But I believe there's not a real reason not to. One of the open questions is whether if you are interested in 3 different classes, whether it's useful to have the self-supervised network create its own set of objects, rather than and then pick the different classes by having different validation sets. That's another alternative for the strategy. There's a question about whether the supervised model seems to favor classifying galaxies because of the training bias. I don't think that's the answer, because the self-supervised model is being given the same classification set. But it is possible that something in the self-supervision is differentiating the galaxies more. And so it's better able to separate out the classified galaxy. Again, I do not know that the supervised model doesn't actually generate better values. We'll know once you all submit your answers. Okay, it's about 11:30. It's a little bit early, but let me ask, are there, if there are more questions in question answer, otherwise what I was going to do is to have you play around in the next 30, 40 minutes with this embedding space and find galaxies you like and see what you find. And again, because you have copies of the notebook, yeah, I'll try to post. That's actually a good point. A good question from Adarsh. I'll post the final statistics on the accuracies once everyone has submitted. So tonight sometime. So I'll try to put that in the module as a text file, so you'll be able to access it since you'll have access to the folder. And you now have a copy of the code, so you can edit, for example, the number of steps. You can edit the number of layers. You can play with the number. Is 128 a reasonable number of encodings, or is there a benefit to having fewer? So definitely play around with things offline, because it's a test. Again, the data itself, is limited. You won't ever get to very high precision. We just don't simply have enough galaxies in this set. But so there's a question from Rashid about the stars being misclassified. So in this particular model, there's not an unclassification, it's a binary classification. There are models in which you give a weight to the classification and you can treat anything below a certain weight as unclassified. That's not currently being run on this data set, but one could imagine running this. So I might ask, there's a question about the choices when coding up the layers. And that's an area that is not in my expertise. So I might ask Philip to give a quick answer to the choices that are made. Maybe. Well, while we're waiting on that, there's a question about classification of stars. The data set is very different for classification of stars. For example, all the morphological information, you would not want the image information, because at least in principle, the stars are all the same. So if you want to classify stars, you'd want to be doing something based on the colors or the spectra. But the same type of model will work. The general architecture, it's the input data sets that are different. And in fact, the same model, I mean, this model is modeled after something that was classifying morphologies of galaxies in Sloan with a self-supervised method. And then we put on top of it our supervised interacting galaxy classification, but some other classification could have been done. So why is everyone getting a slightly different answer? The answer has to do with the training and the embedding space, because the projection that you're getting of the embedding space is different and your choice of objects is different. Each of you sees a slightly different projection of the embedding space, and each of you then will start seeing a different we'll then pick out different sets of galaxies. Because each of you is redoing the training part of the classifier is different. And the training part of the embedding part is different. And so each will get a different answer for which version of the classifier is doing better. I'm going to stick around for another 10 minutes for questions. But again, I encourage you to play with the number of training sets, play with the embeddings, and definitely send in different versions. I'm going to stop sharing the notebook since there's nothing useful in this sharing of the notebook, but I will keep the questions part open.
Yeah.
Yes.
We should make clear the submission system only allows one answer per person.
Yeah. But also, do not obsess too much over your answers, right? There's not a grade. You will not, if you submit something and later in your exploration you find a better galaxy, you have the self-satisfaction of having found a better galaxy, but it's not going to matter. I did want to thank Philip both for creating the module, but for answering the questions. He's done a great job and great work. And I think we've already gotten some interesting results. I'm looking forward to finishing with the full 1,000,000 galaxy sample because there will be some very interesting galaxies. One of the advantages of working with galaxy clusters is that these jellyfish galaxies, which are actually quite rare in a survey like Sloan, are much, much more common because we targeted the regions where the gas density is much higher. And so we will very much increase the sample of those things now. There's a question about getting the same results. If you just run the step where you change X and Y, so the projection is the same, you will get the same results. If you rerun the notebook, you should get a different answer. And the training time, there's a point where there's a variable that sets the number of training steps early on. In the step that took 10 minutes, where it says 5, you can change that number. There's an astrophysics question, right, in my wheelhouse. So the basic idea is that galaxies emit light at certain wavelengths. In fact, galaxies emit light at almost all wavelengths. But as the light travels to us, they're traveling through an expanding universe. And so for galaxies that are far away, the expansion of the universe expands the wavelengths of light by how much the scale of the universe has grown. So if the universe has grown by a factor of 2, the wavelengths are all grown by a factor of 2. Superimposed on that, galaxies themselves have a motion relative to us, and that generates a Doppler shift. So for example, Andromeda, which is actually moving towards us, has a blue shift because its velocity is towards us. Once you get beyond a certain distance, the random velocities of galaxies towards us and away from us, or which are never more than about 1,000 kilometers per second, even in the largest cases, will be much less than the expansion factor, which can be more than 1, right? And if the universe doubles, you get a shift by a factor of 2, which is only possible in velocities once you get special relativistic effects. So for most of these galaxies, I will use the sort of cheap term redshift because they're all far enough away that none of them are blue shifted relative to us. But if you look at the most nearby galaxies, some of them indeed are blue shifted. Adarsh has a question about increasing training time, improving the results to bias the accuracy statistic. Yes, so when you submit, you should submit the result training only 5 times, because otherwise it will shift the values. But for your own edification, you can definitely run as much as you want, right? There's no reason not to. But in what you submit, yeah, submit using the smaller things, because I am curious. This is not a very deep study, but it is a chance to do citizen science in a different way. Prathamesh asks, can we encounter gravitational lensing in the training? The training set you have has no strong gravitational lenses, but the sample from LSST, and even the Sloan sample includes a few gravitational lenses. And they, in self-supervised learning, will show up in their own category. And so you can actually create a classifier that will find gravitational lenses this way. This is a project, it's not my project, but there are other people within the LSST collaboration who are actually working on doing this exact same thing. Yeah, so this data set won't have any strong lenses, but it's not because it's fundamentally impossible. It's because this data set doesn't have it. Ian asks, one of the pictures shows superposition of galaxies. So it turns out there are galaxies that appear to be one on top of each other just because they're in the same direction, but there are also galaxies that are very close together in space. And so sometimes you get two galaxies superimposed, and then there's this type of polar ring galaxies where two galaxies have merged, but because the scales are very different, the outer part of the larger galaxy doesn't really know that it's lost the inner part of the inner galaxy to a merger. And so the outer part just continues doing its thing while the inner part has become typically a spiral, S0 or an elliptical galaxy. Because the merger tends to remove all the star formation in the center. So you actually make an elliptical in the center with a ring of remaining spiral galaxy in the outside. They're really cool things. They're pretty rare. As I said, they're sort of late stages of certain mergers. They require rather special conditions. So the two things have to be similar in mass, but very different in size for them to occur. So that doesn't always happen. But that's something that the network can find.
Just to add on to this, in terms of superimposed galaxies, another kind of tricky aspect to determining whether they're merging or not is you can kind of get a sense of the distance of the galaxy given its redshift. So if you have a very red galaxy, there's a chance that it's actually much further than a galaxy that it seems to be superimposed on. So galaxies of significantly different colors are less likely to be actually merging, but they're just overlapping each other in our line of sight.
And because the self-supervised network has all the filter information, it should pick pairs of galaxies with very different colors as being significantly different in projected space as pairs of galaxies that are similar in color. Then it's up to the classifier rules that you give it to be able to distinguish the two. So I don't know how many we have in this training set, so it may not be particularly effective at doing that. But with a large data set, having the color information actually is quite useful because it does it does allow you to separate things that, you know, if you had a black and white picture might look the same, but have a physical reason not to be as easily connected. Yeah, thank you, Phil. There's a question about the interactions between single and multiple galaxies interacting at the same time. I'm assuming this, you mean single galaxies, because the stars are in our galaxy. They're not interacting with these distant galaxies. In principle, yes, that if you have enough objects, the distance space between something that has three galaxies that are all colliding and something that has two, there are fewer such cases. And so there's a question of how many of them are in this training set and how well will the self-supervised network really be able to probe that portion of the space. Again, the larger the number of things you have it train on, the more it fills out this embedding space, and the easier it is to find things that are truly similar.
Also, as we kind of saw earlier, there are there are single stars in the image data through the survey, but through different data processing techniques, we can uh, pretty easily determine what is a star and what is a galaxy. However, there are kind of some artifacts that stars leave, kind of like glare, which do sometimes get classified as galaxies. Um, and that's why you saw that the star ended up with not just in the data set, but also multiple images of it. ended up in the data set. And that's because those are very hard to tell apart from a galaxy outside of manual confirmation.
I believe, and Professor Gateskill can confirm that the recordings of the modules will be available.
We won't post after the end of the school, but they will be out on the Brown Physics YouTube channel, and we will have the links integrated into the Indigo page.
But by being registered, you also have access to the notebooks and to the PDF of the slides.
Should not be concerned about that going away. We will maintain the shared Google Drive and the Indigo site will, all of that infrastructure will remain accessible, so you don't need to copy everything. There was a question about GitHub. We don't currently intend to put the material into GitHub, certainly not for this workshop. It is always possible that specific speakers decide that is also a way to to help people gain access to their examples. We will update our folders with additional information if that does become available. But as far as the winter school itself is concerned, we don't intend to put a parallel GitHub implementation on it for the time being.
I will point out that the raw images from the telescope for this survey are actually publicly available, but it is about 500 terabytes worth, and a lot of work has to be made to turn them into these galaxy images. So I don't particularly recommend that you go from that stretch, but if you wanted the full data set and had many hundreds of terabytes of free space, you could try that. Okay, I think we're out of questions. So let me thank Philip again, thank Professor Gateskill for the setup, and thank Media Services for the help, and thank everyone for attending.
Yes, thank you. And could I reiterate that it's basically 2 hours and a quarter from now at 2 p.m. local Eastern time, we will be looking at LLM applications within science research, and specifically augmentation, using a specific experiments papers, data is probably wrong, papers, and seeing how we can basically create an LLM that is able to answer questions more accurately on the science associated with it. I think, again, we're trying to mix up the modules so that many of you can get or see examples of many different approaches. But thank you again, Jan and Philip. Outstanding. Love this module. very, very nice.
Been here at Galaxies for a long time.
I have. Having said that, I know the two of you can classify incredibly effectively. But no, very good, very good.
Happy break, everyone.
So I think, Julian, we're going to end the broadcast there, and we'll be firing up again at 2 p.m. local Eastern US for the next module.
That's
Thank you very
correct. Thank you.